We'll recap the last few slides. We had kind of described what a convolutional neural network was. A convolutional neural network was something of this kind. You had several convolutional and pooling layers. Within each layer, you had a number of what we call channels, but they're really maps, right? So the input here has 3 channels, which means you have 3 maps, R, G, and B. And your filters you can think of as 3-dimensional cubes which are scanning along 2 dimensions. The filters are just perceptrons. This entire operation is just one giant multi-layer perceptron, but with lots of shared parameters. Many perceptrons have exactly the same weights. So the whole business of scanning is just a mild change of perspective. And I made a post last night on Piazza. I'm not sure if any of you saw it. I'm going to be using the pictures that we described in the post later in the class. And those pictures will also show up in your quiz. And if you haven't already gone through homework 2 part 1, they are very relevant to part 1 as well, right? Anyway, so the CNN itself looked like this. You had these filters. Each filter produced one map. So the collection of filters produced many maps. And each filter produced an output channel. Each filter worked over the entire collection of input maps, input channels, but scanned only in 2 directions, right? And subsequent to each convolution layer, which actually included a computation of an affine map, which is the convolution itself, and it was subsequently followed by an activation. We saw that typically we use ReLUs as an activation. Now the reason for using ReLUs as an activation is twofold. Reasons are twofold. One is it's kind of biologically plausible based on Fukushima's model. Secondly, even computationally, it's one of the most convenient activation functions to use. Then the convolution layers themselves were sort of followed by pooling layers sometimes, but not always. You had several such blocks of convolution potentially followed by pooling, subsequent to which the final set of maps could be flattened and sent either through an MLP or just a single softmax layer. And having just a single softmax layer makes intuitive sense in that that's just sort of, again, keeping in mind that convolution itself is just a MLP with shared parameters. Making the parameters shared all the way to the final layer really makes sense. It's going to give you a lot more flexibility for a given number of parameters. Now, when you want to train the network, here are all the parameters you would want to train. The parameters of the MLP at the end and each of the filters, which is you're going to have, if you have several filters at each layer, you're going to have to learn the parameters for each collection of filters at each layer. And keeping in mind again that each filter is really a perceptron. So it's got to have a collection of weights and a bias. And then finally, the MLP, whose units are also perceptrons, they have weights and a bias. To learn the CNN, we would just use it's just like a regular MLP. The only difference being the structure of the network. You are training, you're given training examples of images and classes. You define a divergence between the desired output and the true output of the network in response to any input. So, wait. All right, let me pick someone else. Bhuvan, can you actually open your laptop and follow Piazza? My TAs are missing yet again. This is for some reason I have difficulty dragging my students here. I have even more difficulty dragging my TAs here. That's really bad. Anyway, so once we've provided training examples of images and classes, right? You define a divergence between the desired output and the true output of the network in response to any input. The network parameters are trained through standard variants of gradient descent. And gradients are computed through backpropagation, right? We're actually going to go through this whole business of performing backpropagation through the convolutional network in a little bit of detail. So first step, the computation of the loss for a single instance. You just have a output for the network, and then you have a target output. You define a divergence, right? So the problem setup itself, this can be defined because we know exactly how to define divergences and such like. The problem setup itself is going to look something like this. You're given the collection of input-output pair, training set of input-output pairs, and the error on the ith instance is quantified by this divergence, which is the divergence between the actual output of the network, which is a softmax output vector, a probability vector, and the desired output of the network, which is typically a one-hot vector. The total error over the training set or over a batch is going to be the average divergence over all of the instances in the batch. Then, if in order to train the network, we are going to use gradient descent, which means that we'd initialize all the weights and biases, which is the same as saying I'm initializing all the weights and biases of the final MLP. I'm also initializing all the filter parameters, which includes the weights and their biases, keeping in mind that each filter is just a perceptron, right? And then you'd iteratively go back through every layer, and for every filter index, you're just going to be using the standard gradient descent rule. So the key here is how exactly do you compute this derivative. Now, the loss, exactly as before, the loss is just the average divergence over many training instances. So the derivative of the loss with respect to any parameter is going to be the average of the derivatives of the divergences for each of the training instances with respect to that parameter. Again, nothing new over here. And so the key really is how do we compute this derivative, right? Now, here's the network again. The network has some output going out in response to any input. Now, we want to compute this derivative for every individual training instance. So everything I'm speaking of henceforth refers to a single training instance. Now, in response to a single training instance, you get some output. You're going to compute a divergence. We know the backpropagation rules exactly for multi-layer perceptrons. There's no need to go over them again. So you could use these standard backpropagation rules to go back and compute the derivatives at the input to the final multi-layer perceptron without shared parameters. Yes?
Someone just posted that the lecture is not streaming.
Paul, the lecture is not streaming.
Yeah, it is.
It is?
Oh, yeah.
Okay. So,
Where is he looking at?
how's somebody looking at? Okay. It is streaming. Can you go on? Do you mind just going back and syncing with it? I'll continue speaking because we can't afford to pause. All right. So this is the easy bit. There's nothing magical so far. We can just compute the derivatives all the way back to the input of the MLP itself. The real difficulty or the real difference lies in what happens subsequently, because this portion has a different structure than what we've seen in the past. And so we have to figure out how exactly to deal with this. The shared because you have shared computation and the convolution layers, which is an issue. And then you have these crazy pooling layers, particularly the max layer. I mean, they are non-standard, so you have to worry about how these propagate the gradient backwards. So that's what we'll go through. Now, the thing to note is that, I don't know if I can make this work. Observe what happens here. When I'm computing the Z maps for any particular layer, this figure is just showing what happens in one map. But remember that I have the Y's from the previous layer, L-1, and these are used to compute the Z's in the Lth layer, from which I'm going to apply an activation function and compute a Y. This is basically what we do, correct? In order to compute any value over here, I'm actually going to be applying the filter that compute for a single Z map. I'm going to have several of these Z maps. So I'm going to be focusing on just one guy, right? the filter that corresponds to any particular Z map actually has several of these patches which are all different. It's like it's a cube, right? I'm just flattening the cube out. And so you'd be positioning this exactly out here, computing an inner product. You'd be positioning exactly out here, computing an inner product. Positioning this exactly out here, computing an inner product. Summing all of these up, and that sum is going to give you this value, correct? Now, this filter slides. As a consequence of that, take a look at what happens. What are all the Z positions that a given Y position contributes to? Look at the Y position that's in blue, right? If this filter sits on top of that Y for any given position of Z, it's contributing to that Z, right? So here are all the pink is the Z map, the green is the Y, and you can see that that position, that blue box, contributes to every single position in the output map, right, in this particular case. So this means that, and this is not just for one layer, it's actually going to be contributing to every layer. So here is what is happening. YL minus 1 is convolved to produce ZL, and the ZL is put through an activation to compute YL, the next output, right? So if you're computing the derivatives, so these are, so that's the output of the L minus 1th layer. The output of the L minus 1th layer is then used to compute the affine combination for the Lth layer. The affine combination is then used to produce the actual output of the Lth layer after applying the activation. If you're computing your derivatives backwards, you assume that as you're working your way backwards, you already have the derivative with respect to the Y. Even for the, because what happens is once you actually get to the final, if you have your CNN, this goes into the MLP, right? At the very end of the CNN. This first layer of the MLP is just this box, which is the collection of maps after all the convolutions flattened out. So when you work your way backwards, when you have the derivative over here, you have the derivative over here with respect to these Y's. For the final layer of the CNN, that's because that's just the final layer. Before it went into the MLP, you just took the final block and unrolled it. So you could roll it right back, and you have the derivatives with respect to the Y. So far so good. The question really is what happens when you go backwards, right? So we can assume that you have the derivative of the divergence with respect to the Lth layer, where initially L is the final convolution layer, right? Now, from those you want to work your way back, and you want to compute the derivatives with respect to Z, which is the affine combination, and subsequently with respect to the Y in the previous layer. If you know how to do this, you can work your way all the way back to the input, right? Now, this is trivial, because the relationship between Z and Y is just that you took every element in Z and passed it through an activation function. So to compute the derivative of the divergence with respect to Z, you just take the derivative of the divergence with respect to the corresponding Y and multiply it by the derivative of the activation function itself at the Z. So this one is trivial, right? The derivative with respect to Z at any position for any map is simply going to be the derivative of with respect to Y at that position in that map times the derivative of the activation function at that Z. This is straight. The challenge is, how do you compute this guy? How do you go back from Z to how do you go back from the derivative with respect to Z to compute the derivative with respect to Y in the previous layer? Now, I'm going to do this two ways. First, I'll do this with formulae, and then we'll see this with pictures. Okay? So, again, look at this guy. This red element in Y contributes to several elements in Z, right? I'll see if this works. You can see that anytime the yellow patch goes past the red, it's not contributing to Z. So which are the locations in Z that this particular Y contributed to? Can you tell me? Maybe this lady can tell me. So you're supposed to look up, right? the stuff is on the slides. So which are the elements in Y that the particular, in Z, that the particular Y location that's circled in red contributes to? And center, does it? Yes, Prashasti? The top 4, correct? Yes. Keep your head up. I'll ask you the next question. You just earned that, okay? So that position in Z is going to be contributing to these 4 guys, correct? What this means is that, and so this position in, this position in Y is going to, over here, was contributing to these 4 locations in the Z, but not just in that one Z. It was contributing to those 4 locations in every Z, right? Because each of these Z's is obtained from the, incorporates that Y in pretty much an identical manner computationally. So that position in Y actually contributes to those 4 locations in every single Z. And specifically, now this is the key piece, right? Let's focus on one guy, right? If I have something over here, so let's say this is the XY position, right? Then let's say my filter is big enough to consume XY for now. Then what is the weight with which this XY position is multiplied to compute this Z? What would the index of the weight be, right? So let's say this is my weight matrix, and clearly in this example, my weight matrix has to be at least 3 cross 3. Otherwise, that XY is not going to contribute to the first Z, right? So which is the weight that contributes to that particular Z? Maybe you can tell me? So I have this is my Y map, okay? This is my Z map. I'm trying to see, so when I compute this particular Z, the way I would do it is by putting this weight matrix on top of my Y map and computing an inner product, right? So this particular location in Y contributes to this location in Z. Which weight does it get multiplied by? She can tell me. Right? Lulan? Which weight? Look at this figure, right? I'm putting this weight matrix right on top of this guy. So it's going to be this one, correct? And assuming the indexing starts from 0, what is the index of this weight? In this case, it's going to be 2, 2, right? So this is 2, 2. 2, 2 is going to be contributing to 0, 0 through weight 2, 2. Through what position does it actually contribute to the Z over here? To compute the Z over here, how would I be placing the weight on it? I'd be placing it like so, right? So which index on the weight would be contributing to that Z? 2, 1. It's going to be 2, 1, 1, 2, depending on how you index it, right? But you get the idea. It's going to be this one, right? Correct? So that's going to be, I'll call this is X, this is Y. So it's 1, 2. Now look at the relationship between these two. So the index of the weight is going to be the index of this guy minus the index of this guy. So XY contributes to 0, 0 through weight XY. XY contributes to 1, 0 through weight X minus 1Y, right? XY contributes to weight 2, 0 through weight X minus 2Y. So in general, it's going to each YXY affects a corresponding X prime Y prime in Z through weight X minus X prime Y minus Y prime. Make sense to everyone? Right? This is going to feature somewhat quite a bit, okay? But now And this is in all the Z maps. Questions, anybody? So, yes?
Usually when we make a 3-by-3 filter, we sum it up and take the value at the center and then fill up, right?
Not the center. So it's going to be the position with respect. I mean, you'd have to adjust your indexing. I'm assuming you're using the top left. If you're marking it as the center guy, that's just a shift of k over 2, right?
So is this for making the backprop easy?
This is not making the backprop easy. This is actually just describing the backprop. The actual, if you want to shift your indexing by half the width of the filter, then you have a problem, right? In the sense that the shift is going to be different for, you have just an indexing problem. Conceptually, nothing changes. The indexing is going to go beyond the end of the image in some cases. But if you want to mark it as the center, right, then you just have to shift your indices. I'm assuming that it's always with respect to the top left corner. What I mean is, in order to compute this term, I am positioning the window with the top left corner out here. Okay? So now, here's what happens. This is an even more extreme case, right? This particular xy is affecting every single z in every single plane in this example through, again, wx minus x prime, y minus y prime, where x prime is the position in z and x is the position in y. So now, which would be this. So when I compute the derivatives, what happens? That particular position in y affects every single position in z and every single plane, right? So what about the derivatives? When I go back, at how many of the derivatives in z will contribute to the derivative with respect to that y? Every single one of them. If I perturb that particular y a little bit, every one of those z's is going to change. Changing every one of those z's is going to, any one of those z's is going to change the divergence, right? So basically I have to sum over, if I want to compute the derivative, I would have to, with respect to that xy, I'd be summing over all the planes, I'd be summing over all the indices on z, right? And the terms I'd be summing would be the product of the derivative of the divergence with respect to that z times the derivatives of that z with respect to y. This is generically correct, right? And what is the relationship between the z and the y? This z over here, so z0, 0 is going to be, it's actually, it's a plus equals because there are many y terms that contribute to it. But if you look at a specific xy, that's going to be y, xy, I'm leaving the other indices out, times, what was this weight term? So if I want to compute the z, which weight term influences the z when I'm thinking of this xy? It was this one here, right? Remember? That was going to be x minus x prime, x minus 0 in this case. I can just write xy for 0, 0. Or more generally, instead of writing, do you see an eraser somewhere? More generally, instead of writing 0, 0, suppose I wrote this as x prime, y prime. Z x prime, y prime is going to be, it's going to be dependent on y x phi times w x minus x prime, y minus y prime, right? This is the product term that actually contributes to the z. Clear, right? So that's basically what we have now. So what is the derivative of, so if I have a derivative of the divergence with respect to the yxy, right? The derivative of the divergence with respect to z x, wait, no, to z x prime y prime. The derivative of the divergence with respect to y xy, how is that, what is the contribution going to be from this term? Anyone? I have z equals y times w, right? So the derivative with respect to z, y, is going to be the derivative with respect to z times w. Straight up, this is just your standard differentiation rule. So this is plus times w x minus x prime y minus y prime. Right? This is the term that's going to be contributing to the derivative with, wait, I'm getting my, I keep messing my things up. Make sense what I'm talking about, right? So in other words, when I'm computing the derivative with respect to the y at any given xy position, that's simply, I'm summing over all the maps, I'm summing over all the positions in the map, each map, and there's a product term which is the derivative of the divergence with respect to the z at any position times a weight, which is where the index of the weight is simply the difference between the index in the y and the index in the z. Make sense? If it didn't make sense as a formula, we'll go over this with pictures a little bit. But the formulae are not in the least bit complicated. Okay? So this is the final derivative I'm going to get. If I've computed my derivatives all the way back to z, I can use the derivatives with respect to z to compute the derivative with respect to y by summing over all the maps, all the positions in the map, the derivative of the divergence with respect to z times the weight which connects that z to the y, which could be 0 if the y doesn't contribute to the z, right? And the index in the weight is going to be the difference in the indices of the y and the z. Okay? So this is simple. You're summing over all the z maps first. You're summing over all of the positions in the z map. And finally, you have this weight combination. So we've sort of figured out how to compute the derivative given when I'm going back. We had y L minus 1. From these, you applied the weights, and you got ZL, which was a bunch of maps. And from ZL, you got YL through the activation, right? So we figured out how to go all the way back here. And if we had this derivative with respect to the YL terms, then it was trivial to compute the derivative of the divergence with respect to the ZL terms. And from those, we figured out how to compute the derivative of the divergence with respect to the YL minus 1 terms. So we figured out the backpropagation all the way to the y. There's one term missing. The key one is this guy. What is the derivative with respect to the weights? Because these are the guys we are actually trying to learn. Right? Now, in order to compute this, here's something we'd have to look at. What are all the combinations? What are all the relations that any given weight contributes to? So if you look over here, for example, weight 1, 2, right? Weight 1, 2 is used, every one of those arrows is one relation that weight 1, 2 contributes to. Does that make sense? So if you compute the z at 0, 0, that's going to be y12 times weight 12, right? That's going to have y12 times weight 12. If you want to compute the z at 10, that's going to be y22 times weight 1, 2. Right? If you want to compute the z at the third location, that's going to be, you get the idea, right? Y weight 3, 2. So every single y contributes to a corresponding z through this w. So any given weight contributes to the computation of many z's, and in each case it actually uses a different y. Is this coming across? I mean, I don't know if I managed to explain it clearly enough. The figure should be explanatory, right? So now, given this, if I want to compute the derivative with respect to this particular weight, I have to consider all of these relationships, right? So that will give me this guy here. The derivative of the divergence, again, going back to this relationship, if I fix wxy as the thing that I'm trying to compute the derivative with respect to, then you have z of x prime y prime plus equals wxy times what are the indices of x, of y. So again, think about this, right? I have a y, this is a y map. I have a z map, okay? Now, I want to find out, so let's say I took z0, this is x prime y prime, okay? I want to find out which y contributed to x prime y prime through weight xy. So weight xy means that, what are the xy indices over here? That's the shift with respect to the y, right? So which particular y is going to be contributing to which particular position in the y plane is going to be contributing to the x prime y prime position in the z plane through wxy. That's simply going to be, so if you want to compute this one, this is how you would be positioning your weights matrix, right? And if that is how you're positioning your weights matrix, then if you are looking for some xy location in your weights matrix, you're trying to see which position in y contributed to the corresponding x prime y prime. That is going to be x prime plus x, x prime plus y. Make sense? I mean y prime plus y. Does that make sense to you guys? Right? Think of how I'm positioning the filter on top of the y plane. And then you can find out which corresponding location in x actually contributes to it. So this really means that the derivative of the divergence with respect to the weight is simply going to be the derivative of the divergence with respect to z times this y. Right? So the derivative of the divergence with respect to the weight is the derivative of the divergence with respect to z times the derivative of the z with respect to the w, which is simply the derivative of the divergence. Again, you're summing over everything. So the product term is looking at one particular contribution, right? The derivative of the divergence with respect to z times weight x prime plus x, y prime plus y. Make sense to everybody, right? So the arithmetic is straightforward. This particular one, the arithmetic is very, very straightforward. No big deal. So here's how you get. Now, observe that when you're computing the derivative with respect to a weight, you have a separate weight for each map, right? So when you're computing the derivative with respect to the weight, you're not summing over the maps. The weights are different for each map. All you only have to consider one pair of maps, one y and one x. But you do have to sum over all the one z, but you do have to sum over all the positions in the z. Right? Okay? So if I were to, but this is all very complicated looking, right? If it's very complicated looking, then there must be an easy answer. And there's a very, very easy answer. Forget the math, look at the code. And here is the simple trick that will never fail. So if you don't want to work out the math, you're no good with your arithmetic, you get tangled in your indices, and you get very confused, and then you have to go and have coffee, then don't do the math, right? Write code. Look at what happens when you go forward. Here is a relationship. If I have A equals B times C, right? Then dF over dB equals dF over dA times C. I can just do a plus equals if there are many contributions going in, correct? And dF over dC is simply going to be dF over dA times B.
F is a function of A.
Yeah, F is a function of A, right? So in this case, you see exactly, this relationship is trivial. This was the first, very, very first derivative you ever wrote when you took calculus, right? That turns out that's all you really need to know. And there's so much complicated looking arithmetic over here, I can ignore it all. How so? Let's go back and look at the forward code for the CNNs. So here is the forward code for the CNNs. Look at what I'm doing. There's nothing about CNNs. What I'm writing over here applies to every single neural network code you would ever write. Okay? So this is the forward code. I'm going over all the layers. I'm writing this in convolutional format. Then I'm going over all of the perceptrons, the filters. And in each perceptron, I'm scanning the input. When I'm scanning the input, what am I doing? I'm going over the image. I'm going over X and Y. At each location, I'm pulling out a little slice of the image, positioning the filter on it, and then I'm computing an inner product. But the inner product, what is the inner product? I'm going over, so I have the original image, and I'm scanning it. At each position, I have got this little location, which is my filter. And over the filter, I'm scanning, which is the indices, the scanning over X prime and Y prime, right? And I'm taking a component-wise product. So W times Y, and summing those to compute my Z, right? This is your forward code. Nothing really has happened over here. No magic, right? But then I'm going to use this trick. Look at what happens. Here I have Z equals W times Y, right? So the derivative with respect to W is going to be the derivative with respect to Z times Y. The derivative with respect to Y is going to be the derivative with Z times W. Right? We haven't even looked at the math. I'm just looking at the code. So now I can just write my code like so. I took my forward code as is, took that one line and split it into two, and I replaced this one line with these two guys. And I got my, it's a plus equals because there are many terms contributing, correct? And I just got my derivative. So we've seen the math, we've seen the code. The math looked complicated, the code is trivial. You literally just take your forward code and replace it by a little change, and you're going to get back your derivative code. Questions, anybody? Right? This makes it so simple, right? When you begin thinking of it this way, that all that ugly, complicated looking math just disappeared. So, and there are multiple ways of actually rephrasing this in vector format, but this is the basic code when I'm actually doing this with loops, right? And now here is the magic. I can do the same thing. All the math that I explained, if I changed my strides, you had to go back and worry about what happened. It turns out that if I'm looking at it from the perspective of code, I don't have to worry about it. Here is the forward code. So if I want to do this with strides, just remember what we did in your forward code with strides. I'm just going to take my forward code as is, and just replace the location where I computed the derivatives with respect to where I computed the z's, and replace every line that has this format with 2 lines of this format. And that's actually going to give me the derivatives. Right? And there's nothing about neural networks. You can apply this pretty much anywhere in anything you do. Later in the course, we'll actually look at how you could literally write a little function to compute derivatives for any ugly odd function. So remember, you do the autodiff, which is part of your code. You can write your own autodiff. Maybe you should, right? And you'll see how you can do this. It's very trivial. So, but then so we've seen how this works with code. Let's look at pictures, right? And pictures are great, particularly because I can animate them in some manner. Now, look at this guy. This xy, right? The y plane, I'm computing the z from the y. So I've marked an xy, and I've marked the same xy location in the z, right? So going back, I've also color-coded my filter. So every position in the filter has a color code. So I have 9 locations. They have 9 different colors. Okay? The color you can think of as being indicative of the value. Now, something interesting happens over here. So look at this. I'm going to compute how each xy in y influences various locations of z. Okay? So look at this. Suppose I want to compute z00, right? z00, if I look at the corresponding xy, I'm actually multiplying the corresponding xy location, which in this case is 22 by weight 22, right? So in general, if I'm looking at a weight 22, that's always contributing to zx minus 2, y minus 2. Correct? Make sense? Where did that color go? So this weight 22 got applied in computing z00. Take a look at the picture, okay? Follow the colors. And now I'm going to take, so I have zx minus 2, y minus 2. I'm going to ignore the other indices for now. And I won't mention the plus. Any time I say equals, I'm really saying plus equals, okay? So z by x minus 2, y minus 2 equals yxy times weight 22. You can see how that happens, right? It's exact, and I've shown the color code. The color actually explains this. You can visualize this, okay? So I can go back and write the derivatives. The derivative of the divergence with respect to y is going to be the derivative of the divergence with respect to zx minus 2, y minus 2 times w times weight 22. Right? So nothing fancy. Yeah? Now, I take a step forward. When I take the computation moves one step forward, the entire filter has slid forward by one step. And now which z position are you computing? The z position you're computing is 1, 0, right? Which weight do you use for it? That is the pink one, 1, 2, right? So z in general, for any xy, zx minus 1, y minus 1 is based on yxy times w12. Right? Look at the location of the color, okay? And I can keep computing this forward. I go to the next one. I'm going to get, and again, going back, this is the key piece, the derivative, okay? So the derivative of, with respect to xy, now has an additional contribution with respect to, of the derivative of the divergence with respect to zx minus 1, y minus 2 times weight 1, 2. Okay? Then I can slide the whole thing one step forward, like so. And now I'm computing z20, or generally zx minus 2y, right? So zx minus 2y is going to have yxy times w02. So therefore, the derivative of the divergence with respect to yxy is the derivative of the divergence with respect to x y minus 2 times w02. Now observe that in all of these equations that I'm writing, this term has always stayed the same. I'm just adding contributions to it. It's always the derivative of the divergence with respect to yxy, right? So now here the contribution is through zx minus 2, y minus 1 times weight 2, 1. Zx minus 1, y minus 1 times weight 2, 1. So you can see exactly what's happening. Observe what happens to the right, right? But here is something else that happened in the process, okay? Take a look at the colors that I've imposed on the z. Okay? Each xy contributes to a corresponding z position, but look at the pattern of weights. The pattern of weights is left to right, top to bottom, inverted with respect to the original weights. Right? So what this means is that when I am computing the derivative of the divergence with respect to xy, I'd be going over all of the planes, of course, but now I have to compute the contribution of every z position, but the contribution of any z position is going to be the derivative of the divergence with respect to x minus y x prime, y minus y prime times wx prime y prime, right? Which is basically to say the derivative of the top left corner times the red weight plus the derivatives of the top second corner times the pink weight times the derivative of the green third corner times the green weight, and so on. So basically what has happened, I've used the z derivatives map of the z as is, but I flipped the weights bottom to top, left to right, and then computed the inner product. To compute the derivative with respect to y, and now here is the crazy bit, at the bottom right corner, not at the top left corner. Remember, when we were going forward, I was imposing the weight on the y map and computing the z at the top left corner, right? Now I'm flipping the weights, imposing it on the derivatives of z and computing the derivative with respect to y at the bottom right corner for this particular guy, right? So what does this whole thing amount to? This, basically, the derivative with respect to xy is obtained by flipping the filter left, right, top, bottom, and computing with such that the filter is positioned with its bottom, the flipped filter is positioned with its bottom right corner at xy. And then you compute the inner product. The inner product of the weight, flipped weight, with respect to the derivative map. So everybody see what I'm talking about, right? I'm drawing this with pictures. You can go back and see this. So if I were to compute, so let's go back and actually sort of compute the entire derivative. The top figure on top is the filter, the original filter. I've flipped the filter left, right, bottom, top, bottom, and so that's the rectangle, the square shown in the middle. That's just the flipped filter. And now to compute the derivative with respect to y, I'm going to start off with the derivative with respect to z. I'm going to flip my filter and look at how I'm computing it, because I'm talking about the bottom right corner of the inverted filter, correct? So this is how I would compute. I'd position the filter on top of the z derivatives to compute the derivative with respect to y at that location. Okay? Now to compute the derivative with y at the next location, I'm going to slide the whole thing forward one step and position it like so. And so I can do this. Observe that the filter actually goes outside the inverted filter actually goes outside the map. Right? So is this making sense to everybody, the way we are actually performing the computation here? This is exactly what's happening, right? Now I've shown you only one map. In reality, what happens, each location in y contributes to all of the maps. So you'd actually have to be computing derivatives with respect to all of the maps. And so in order to compute the derivatives with respect to all of the maps, here's what you would do. Let's say this is your filter. The filter has several planes, one per y map, right? You'd be flipping each plane locally, left, right, top, bottom, okay? And so this is going to be your flipped filter. This is just the equation for the flipped filter. And then this is how you'd actually compute your inner product. You're going to be placing the flipped filters on the collection of z maps and summing the inner products to get the derivatives at the various locations. Is this making sense? So now once you actually see what is happening, it's trivial to conceptualize what's going on. Skip the math, right? This is just a convolution of the derivative map for the z with respect to the flipped filters. But then you have to do something with the derivative maps for z. What is that? The filters go outside, right? So you have to zero pad it. How many zeros will you add on each side? K minus 1. If the width of the filter and the height of the filter is k, you're going to be applying k minus 1 zeros on every side, right? And so if you were to write pseudocode, here's what you're going to do. This is the code. The first thing I'm doing is I'm going through all of the filters and flipping them, all of the planes in the filter and flipping them, just being very explicit. The z shift, I'm calling it a shift. You'll see why if you look at the slides, but you don't need to think of it that way. It's simply the zero padded version of the z. And then the bottom code is literally just a convolution. So what happened was, it turns out that computing the derivative with respect to y is also just a convolution. Except it's a convolution of the derivative of the z map expanded out to be the same size as y plus the size of the filter with the flipped filters. Right? Make sense to everybody? Yeah? So we've seen how, so now what we've done is we've gone through the mechanics of computing the derivative with respect to the y and computing the derivative with respect to the w. And it's very straightforward. Now, as it happens, this is actually also part of your homework, so it was good to know. Now, there's another operation that happens, pooling and downsampling. Pooling is typically performed with strides greater than 1, results in shrinking of the map, which is why we call it downsampling. What do? At each location, you pick the max in a bunch of locations. And this is by plane, right? You're not mixing between planes. But this is how you would compute the max pooling. You're going to take a block and pick the max guy. I can write the equation like so. I can say each max operation consists of two operations. First, I find the location of the max. Second, I read the y value at that location, right? This is the max operation. Now, computing the derivative ends up becoming a bit of a pain. Why so? Because max is not a differentiable operation by itself, right? But then if I have something like this, I have this little block that I looked at when I was performing max pooling. Then I only pick the max. And the derivative is literally saying, if I perturb this value a little bit, how much does it change the output? And that answer is going to be 0 for everything except the max, right? So which means that the derivative with respect to the z, or the derivative with respect to the max pooled output, is going to be transferred wholesale to the one location that was picked. And the derivatives for the other guys are going to be 0. So the derivative is going to be the same as with respect to y, is the same as the derivative with respect to u, which is the max pooled version, at the peak location, and 0 everywhere else. Make sense to everybody, right? So if I were to write pseudocode for this, it's very trivial. In the forward code, when you're doing max pooling, you're keeping track of the locations of the max position for at each point. And then you're just reading the y's at the max position. In the backward code, you would just contribute. Now observe that you're using plus equal to, because if your max pooling filters overlap, a single y might contribute to multiple locations, right? But you're only incrementing the derivative at the location that contributed to the max. The rest are not being incremented. All of this pseudocode is assuming, it's written assuming everything has been initialized to 0. Okay? You can replace max with mean pooling. The mean is simply taking the average of all of these guys and sticking it in. Remember, the max was a biologically motivated operation. There's nothing magical about it for a computer. The mean may be a more robust statistic. Turns out it's not, but then you can also have other kinds of functions which you're computing on this collection. But specifically, let's look at the mean. The mean is just the average of these four guys in this example, right? So now when I get a derivative backwards, so it's going to be 1 over k squared because you have k height and k width. And you're summing all of these guys. When I compute the derivative backwards, I get a derivative all the way to u. How does that derivative at u get transferred to the block of elements that were considered for the mean? It just gets uniformly distributed across all 4. I mean, obviously, right? So that derivative going backwards is simply going to be shared between all 4. So here you take the derivative divided by 4 or divided by k squared and add it to every one of these terms. So if you go back and look at the code is just going to be, once again, this is the forward code. At each u, you're looking at the mean of a block of y's, right? The backward code, you're just going to be taking the derivative. This should have been a du, I'm sorry. The derivative with respect to u divided by k squared is summed back, right? Okay. And so over here, we've looked at how to compute derivatives for every kind of operation going back from the end to the beginning, right? Which means you are now able to compute the derivatives everywhere and perform backpropagation. Questions, anybody? Right. You've seen the mechanics of it, and we've seen the math of it. The mechanics of it, we've seen it in 2 different ways. The trivialist thing to do is to simply take your forward code and just flip a few things around, and everything will just work, right? If you can write forward code, you can write backward code without even knowing math. That is a take-home lesson, right? Now, so the story so far, the ConvNet is a supervised version of computational models of mammalian vision. The parameters of the network can be learned through regular backpropagation, where you just take care of the specifics of shared parameter computation and some peculiarities like max and mean, right? So now, there was one implicit assumption in all of this. We assumed that as you went through the network, the size of the output always shrank, right? Is this necessary? In a multi-layer perceptron, the size of the output, the network is not pyramidal. It can actually, remember, the convolutional neural network is just a standard MLP with shared parameters, right? If it's a standard MLP with shared parameters, an MLP does not need to have a nice pyramidal structure. More often than not, your network will expand and then contract, correct? Just so that you can actually get more detail into your model. So how would you apply that concept to a CNN? So when I talk about it in terms of CNNs, right, and convolutions and downsampling, the fact that in an actual MLP, there's no restriction that the network size has to keep decreasing layer to layer, that doesn't really come out. Now, to really take advantage of that, you have to consider how the entire operation will be performed. So I'm going to show this using 1 dimensions. I'm assuming that you actually saw the Piazza post from last night. How many of you did? Okay, the rest of you have no clue what I will be talking about in the next 5 minutes. Okay, but follow this and maybe go back and look at the Piazza post. But we've also seen this figure before yesterday's Piazza post. Where did we see it? Somebody mumbled, yes? Yeah, but no. So we've seen this kind of figure in the lectures previously. Where? This will tell me how many of you actually go back and actually look at the slides.
The multiple scans combined in the single network.
I have exactly the same figures in lecture number 1, I think. So clearly you haven't gone back and looked at the slides, right? Go back and look at the slides. I'm going to assume that you saw the slides. I'm going to talk as if you did. And I'm going to assume you understand everything I say. If it doesn't make sense, go back, look at the slides, come back and look at these slides again, okay? So now, this figure here shows you a standard CNN, okay? I'm talking about a one-dimensional convolution over here. You can generalize this to 2 dimensions. And we will see in a bit. Now, so I have time. These are all the inputs. Every bar represents a vector. Imagine I'm scanning the input with 2 neurons in the beginning. And when I'm scanning it, I have a stride of 2, right? So for every 2, I'm going to get, every 2 inputs, I'm going to get a pair of outputs, right? So I'm representing that with this vertical bar. And that's scanning, right? It's jumping 2 because this stride is 2. What this means is that every component of this vector connects to every neuron in this bar, okay? Now the result is going to be a sequence of bars in my representation. And how many such bars will be there? If I have n inputs, it's going to be about n over 2, plus or minus 1, depending on whether it's even or odd or whether it's 0 pad, right? And so then the next layer, I'm scanning this collection of bars with a set of 3 filters, 3 neurons, right? So I'm showing those 3 as a bar. And in this case, I have a stride of 3 at the next layer. So that guy is connecting to all of these inputs, all 6. Every neuron in the second bar is connecting to every one of these 6 neurons with different weights. And the collection is being computed, the bar, and then you're jumping forward 3, and you're repeating the process. So the second bar is scanning the output of the first layer of the layer of filters. The next bar is, and the pink bars are scanning the output of the second layer of filters, and so on. And then all of their outputs finally are used to perform your softmax, right? So I'm going to use this simplified notation where each arrow means that every component at the input connects to every component at the output, okay? Observe the structure. This is the kind of structure. Now the colors show parameters, right? The colors, I have no shared parameter indication over here. But think this guy, this set of weights is going to be identical to this set of weights, is going to be identical to that set of weights, correct? So also this set of weights is the same as this set of weights, is the same as this set of weights, is the same as this set of weights, and so on. And these weights are the same as these weights, are the same as these weights, and so on, because you're scanning. They're basically, I've drawn it as an MLP, but it's really a shared parameter network. There's also a scan component. The entire thing can be seen as one giant multi-layer perceptron, right? Now, this multilayer perceptron, because our strides are always 1 or less, it's pyramidal, right? Now, if I want to increase the size, what do I do? At some point, I'm going to add a layer which has more bars, vertical bars, than the layer underneath. This is going to increase the size of my output, right? But when I add a layer which has more bars than the number of bars in the layer underneath, I have to worry about how things are computed, keeping in mind the symmetrical structure of a shared parameter network, right? So here, I have literally arranged the vertical bars such that there is symmetry. There has to be. Otherwise, this is not going to be feasible, right? You won't get a nice shared parameter structure. And now the difference here is that when I have a shrinking network, then the set of incoming weights is always the same. So the set of downward weights from this guy is going to be the same as the set of downward weights from this guy is going to be the same as the set of downward weights from this guy, okay? But at any point, if the size of the network is increasing, then it means the way I will design it is that the set of outgoing weights from the bars underneath is identical for every bar. Okay? So the red collection of purple bars, purple arrows, has the same value for every vertical bar. And so now the computation would proceed as follows. If you started from left to right, this guy has already been computed, partially computed. Now this term, this bar is contributing to those 3 bars. Then the next guy is going to contributing to those bars. So they get incremented. If you have multiple inputs coming in, they contribute, right? And so on. And this is how the computation would proceed, right? So there's one. This is often called a transposed convolution. Why? You can think of this as an MLP, right? When I'm thinking of this as an MLP, I can write z equals w times y, which is the affine combination, ignoring the bias. If I have a shrinking network, w is going to be wider than its tall. If I have an expanding network, w is going to be taller than its wide. You can think of a tall, wide, tall matrix as the transpose of a broad matrix. And so you like to think of this as a transposed weight matrix. Is a transposed convolution. A regular convolution is going to be narrow and broad in terms of the number of bars. A transposed convolution, when you transpose it, you're going to have more outputs than inputs. So it's like convolving with a transposed weight matrix. So you like to call it a transposed convolution. You can do the same thing in 2D. So here, I would like to go from a smaller map to a bigger map. The computation is exactly the same. So here, for instance, I have all of these y maps, and I want to go to a z map where the z map is larger than the y map. Okay. So again, now the set of outgoing parameters is going to be shared, right? And if I want to go from a map of size 5 by 5 to a map of size 10 by 10, that means I'm going to be scanning the input, but the outputs are going to be strided by 2. So what does this mean? Take a look at this computation, right? So I have this bunch of filters. I have the y. I'm going to be computing the z. So the first thing I would do is I'd take the first component of all of these y's, multiply those by the z's. Remember, when you had a shrinking network, you placed the z on the y, correct? Here I'm going about it the other way around. And you can have any kind of combination in between. So I take the first y multiplied by the first weight matrix, the first y of the second plane, multiply that by the second weight matrix, first y of the third plane, multiply that by the third weight matrix. The resultant is going to be the size of my weight matrix. I position at the top left corner of my output, right? And then I'm going to go forward 1, and I take the next y, I compute this, perform the same computation, and I increment the output map, but now I've strided by 2, right? And so if I go forward in this manner, like so, I'm actually going to create an output map which is bigger than the input, and this is just like expanding the size of your MLP. Okay. So here is the expanding convolution layer, and the pseudocode is there for your reference. I'll just keep it there, leave it there. Okay. Also called transposed convolution, because if you recast the CNN as a shared parameter MLP, expanding layers have weight matrices that are taller than they're wide, and so it's like a transpose of a regular weight matrix. Okay. Now, what a CNN really gives you is shift invariance, right? So you want to say, I want to find a flower regardless of the location of the flower. That's what you have. That's what we started this whole series of lectures with. But now I want more invariance, right? I want to get the same. I want to find the flower not just regardless of the position, but also regardless of the size of the flower. Will that basic network work? Not really. It's looking for a flower of a specific size, right? I want scale invariance. I want rotation invariance. Will that basic network work? It's not going to work, right? So you also want to rotate to have rotation invariance. So in general, you want some transform invariance, right? Now, so a different perspective of shift invariance is that you're looking for a pattern of a specific size, which is shown by your filter, and you're scanning your input, right? Now, if I want to also find a pattern, the same pattern but of a different size, what would I do? If I think of my filters as the basic pattern that I'm searching for, then what would I do? It's like scanning for a flower, right? If I want to find a bigger flower, what did I do? Increase the size of the flower pattern that I'm looking at, right? I can take my filter, I can expand it in size and rescan. Suppose I want to find a rotated flower, what would I do? I take my flower and rotate it. I can rotate my filter. Correct? So there's an entire collection of transforms that I can permit. I take my filters, the basic filters, and create many copies of it. It's the same pattern. So I won't have different filters for different sizes. It's the same pattern, right? I'm just going to put that filter to different transforms, a rotation by 45 degrees, a scaling by a factor of 2. And I'm going to scan by each of these guys. And I'm going to get a whole bunch of different maps on which I'll be performing my operations. Right? So what this means that each filter produces a set of transformed and shifted maps. So I'm going to be producing, the set of transformations must be enumerable and discrete, otherwise this is not going to happen, right? But if I do that, then from each filter I'm going to create many clones, each transformed in a different way, and then I'm going to perform my scan. Yeah? I have to enumerate my transforms. So if I were to write my code, I can actually just say, here's your regular CNN for one layer. We've seen this before. All I did is, instead of just going through all of the filters individually, all of my perceptrons individually, which is in the 1 to DL loop, for each of those guys, I computed every transformed version of it. So I'm going over the complete set of transforms, and then I'm just scanning over the entire input using those transform filters. Questions? Right?
How much to transform?
That's a design choice, right? You're enumerating the transforms. You might say, I'm looking for flowers, but I also want flowers that are rotated by 20 degrees. I'm looking for flowers, but I also want flowers that are scaled by 1.2. So that's your design choice. This is not something that's learned. That's not general. So the set of transforms that you choose is your choice. Right? We don't normally use these, but if you want it, you can plug it in, yes? The concept remains, yes?
The weights will be shared between the transform filter.
Here's what happens. Every one of those transform filters are basically derived from the original set of filters. So when I'm computing my derivatives, I can compute my derivatives till the transformed filters, right? But then I'm going to have to go back through the derivative of the transform, the inverse of the transform itself. And all of these will contribute to the derivative of the original filter, which is going to be updated. Right? So because they're all different copies of the same filter. But otherwise, the whole concept still holds. Exactly. Now, the inverse doesn't have to be a mathematical inverse even. You just need to find for each point in the transform filter, what was the corresponding point in the input filter, and that should take care of it, right? So the story so far, continuing, CNNs are shift invariant neural network models for pattern detection, which are equivalent to scanning with shared parameter MLPs. The parameters can be learned through regular backpropagation. Like a regular MLP, individual layers may either increase or decrease the span of the representation learned, and the models can be easily modified to include invariance to transforms other than just shift. Yes?
I have a question. Instead of expanding the filter, couldn't you just contract the original input image
They're equivalent. The whole point is if I'm having a whole bunch of different transforms, I'm going to end up with maps of different sizes for the next step.
Wouldn't it be easier if you just did the transform on the input instead of doing it on the network?
Here's the point, that if you transform the input, I'm going to end up, I'm just speaking of a single filter, right? But my next position is going to say, I can find a petal or a slightly rotated petal and a sepal. So in order to do that, you want all of the maps to be the same size.
Right.
If you transform it, they're going to be neither the same size. Transform the input, the transformed inputs are neither the same size nor the same orientation, right? So that's why we would do it with the filter and not the input. Computationally, at one level, at one layer, they're all equivalent. But when you begin combining things, it's going to break down, right? Now, what about the exact location? I'm scanning for flowers. I've found that this picture has flowers. Where are the flowers, right? That was never answered. Now, turns out you can actually do something simple. I can find the bounding boxes. If there's only one flower in the image, then I can take the final representation and add an extra layer, which produces a bunch of outputs. In this case, it's going to be 8 outputs, which are the xy coordinates of the 4 corners of the bounding box of the flower. And now when you train the network, you jointly train to minimize both losses, not just the ability to detect that there's a flower, but also the ability to find out the exact location of the flower, right? And you can do the same thing for pose estimation. How many of you have just gone past that corridor from Hillman to Nouvelle Simon and appreciated Yasser's demo over there, where it shows you a skeletal structure, right? It's scary. It's not so. You can do it. You guys can do it, right? You know exactly enough to do it. All I have to do, I detect the person. So the upper layer of the network is going to tell you if there's a person in the image, or how many people there are, right? And the second one, you'd have to expand it for multiple people, but the basic idea remains. And the second one is going to give you the xy coordinates for every one of the joints. And once you have those, you can just go ahead and build the skeleton, right? Questions? So, and you have other kinds of variations. You have very deep networks, convolutional networks with hundreds of layers or more. There's a formalism called the ResNet, which you will almost certainly encounter in your homework. If I have time, I'll go over that briefly. But first, there's something else that you will actually end up encountering a whole lot more. I hope you don't mind my going 4 minutes over, because this is an interesting and important concept. You're going to encounter something called depth-wise convolutions. It turns out that when we perform our convolutional neural networks have a whole bucket load of shared parameters in an attempt to reduce the total number of parameters to get a certain representation power, right? Otherwise, you could always not share parameters and say, I'm going to learn to detect flowers here or there with a ton of parameters, and that would work. But you took advantage of the fact that regardless of where the flower occurs, it looks the same. And you came up with a shared parameter network that resulted in a scanning kind of concept. In spite of that, the number of computations can end up being really large. Number of parameters and computations can end up being really large, because you're going to be scanning with each filter. Scanning with each filter is computationally expensive, right? Because you're scanning as many times as there are filters. And secondly, you're going to have require parameters for every single filter. So can we actually get rid of this? It turns out you can. And although in principle you would be reducing the number of parameters and therefore reducing the power of your network, it turns out to be more effective in most cases. To see how this works, look at what happens in a single regular convolution. In a regular convolution, you have so I have many y-planes, correct? And for a single filter, I have the corresponding component filters for each of these planes. To compute the z position at any location, I'm placing this guy here and computing the inner product, summing up, and then adding this, right? So what did I do? I placed the z there and then summed up, and I placed the filter there, summed up, and then immediately computed the z location. I can do the same thing slightly differently by changing the sequence of operations exactly as we did for CNNs. And how would I do that? I can go ahead and I can just, with each of these guys, I scan the input, and I'm going to get a scanned output. So I'll call this Z1, right? And then I can sum up these locations. And that's going to give me my final z at this location. It's the same operation done differently. I scanned each of the planes first independently, then added up the corner location. I do this for every location, right? Same concept. So each layer of each filter scans its corresponding map to produce a convolved map, and then all of the convolved maps are just added together. This is for one filter. And so if you have a collection of filters, each of those guys is going to be doing exactly the same. Each of the filters is producing its collection of maps, and they are being added up. Now here's a magic thing. This is another room for sharing parameters, right? Instead of having different planes being produced by each filter, I can have one common set of planes being produced. And the different maps will only differ in how they weight these different planes in combining them. Right? So this is a shared parameter version of the original computation. For some strange reason, they call it depth-wise convolution. There's no convolution across depth. The real operation that's going on is exactly what you see on these slides. Right? You just, instead of producing many planes, one per filter, and then summing them up, you produce one set of planes, you sum them up in different ways to get different output filters, different outputs. Right? Make sense to everyone? Yeah. Okay. So it turns out that there are many, many advantages to this. One, of course, is immediately apparent. If you look at these two guys here, I had to do the convolution 3 times. Here I had to do the convolution once. So there's going to be a large reduction in the number of times you're performing the convolution. But much more than that is the number of parameters. So here if I have a different collection of filters, if I have n independent filters and there are m input channels, and the filter span is k cross k, I have m times k cross k times n, right? That's n k squared parameters. I'm not even counting the biases. In the second case, I'm just going to have m times k cross k because I just have one common filter, right? And then I'm going to plus n times m. There's mk squared parameters plus n times m, which is the different ways in which you combine them to produce the maps. So there can be an order of magnitude reduction in the number of parameters as well. Right? So there's a lot more to the story so far in the rest of the slides. Take a look. I'll just stop with the story so far. CNNs are shift invariant neural network models for shift invariant pattern detection. The parameters can be learned through backprop. They can be easily modified to include invariance to other transforms. They can make predictions related to the position and arrangement of target objects. And several variations on the basic model exist to obtain greater parameter efficiency, better ability to compute derivatives, etc. Now, do me a favor. Go through the rest of the slides. The next time I come and ask you, have you seen this figure before? And it's been in one of the hidden slides, I expect to hear a yes. Right? Don't fail me. See you next class.